basically is a collection of characters. These characters could actually even be Unicode characters, so you can have smiley faces and stuff in there. But sort of by default, it's going to be just characters, uppercase, lowercase, numbers, punctuation, that sort of stuff. And so because of that, it is sufficient to think about these things as being stored in ASCII, even though they're actually truly being stored in Unicode. And we looked at an ASCII table, so let me remind you of that, and let's just have that handy for posterity's sake. So text originally was stored in this, let me scroll, here we go, this format, okay? And the printable characters start at decimal number 32 or hexadecimal number 20, depending on which way you count. And this is the arrangement that we've used, well, basically since the 60s. So it starts with a lot of the punctuation symbols, then we've got all the digits, and then we've got the uppercase letters start at decimal 65, going to Z. Then we've got a couple of more punctuation or symbols. And when there's multiple ones in a row here, the rightmost one is the current one. So there was a little bit of things changing over time. Then the lower cases got added in there. And then, the tilde and a few other things. So it was originally a 7-bit scheme, and so you could only encode 128 different things with this, which was good enough for early computing, but there were sort of two problems with that. One, 128 characters is not a whole lot. If you've got 26 letters in the Latin alphabet, you need really 52 of them because you've got lower and uppercase. You've got all the digits, there's 10 more, punctuation symbols, and we spent 32 of these characters on things like the line feed, carriage return, and stuff that's sort of the legacy of the typewriter era. Okay, so that runs us out of that 128 pretty quickly, right? And in particular, what's missing? I mean, there's lots missing, but what comes to mind is stuff that's missing. Yeah. Punctuation's there. So we've got like period, exclamation, semicolon, those sorts of things, but there's still stuff missing. Thomas? Right. So symbols from other languages, right? This is basically very English-centric in the sense that there's no accented characters, accented Latin characters even. So you can't even do Spanish in this because in Spanish, right, it's mostly the Latin alphabet, but then there's the N, for example, there's two versions, right? Regular one and the one that has the tilde above it, right? And what's the difference in terms of pronunciation? Regular N is just N. What's the N with the tilde above it? Yeah, it's an NY kind of sound, right? So, yeah, so you can't do that in standard ASCII. Now, it was very, very quickly extended to an 8-bit scheme, okay, which is called extended ASCII, and we'll go here just because it probably has the table more easily viewable. Well, you know what, let me just do this. Okay, let me zoom this out so we can see everything. Okay, so this is standard ASCII. It's the first half of the table, right? Which is the printable characters, and like we said, it's very American English centric, right? There is a tilde, but there's not an N with a tilde above it. Or like in French, for example, there's the C with the little dangly bit at the bottom called the cedilla. You don't have that. You don't have yeah, any of the other stuff. Okay, so very quickly, this an eighth bit was added to the scheme, and that allows us to get basically all of the different accented Latin characters that you might need for essentially most Western European languages. Okay, so Spanish, French, and so on. And then we've got a couple of the fun ones like the AE symbol. That one's one that we don't use particularly often, especially not in English. But you've got the other ones, you know, like uh, the E's and stuff that have the different accents of it, and the A with the little circle above it. I think that's what in like Swedish or something. Okay, so you can get basically any of the Western European languages out of this. There's some extra currency symbols like the pound symbol, the cent symbol, the yen symbol, and I'm not sure what that is. It's a little hard to read. Um, huh? Okay. Uh, yeah, who's the Russian spy? We just found him. Okay. Um, Also, a couple of like fractions. Um, Characters 174 and 175 are how they do quotations in French. They don't use the standard quote marks like we do in English. And then there's some of the mathematical symbols. It's not the entire Greek alphabet that's there, but the commonly used letters that appear in mathematical work. So alpha, beta, gamma, pi, sigma in both versions, mu, right, for the mean if you're doing probability, tau, phi, omega, capital in this case, an infinity symbol, and a few other things there. So that's great, right? We've added some, but we're still short. Namely, like the main problem, right, is how would you put Chinese in here? You don't, right? Because how many characters are there in Mandarin, say? There's thousands of them, right? And so this scheme is not going to work, and that's just Chinese symbols. Okay. Now, granted that they get sort of reused in some senses in Japanese and sort of classical Korean, um, but it's still thousands of them. Well, what else do we? What other languages might we want to do? There's, ancient Egyptian hieroglyphs. How many of you guys find yourself in the situation of needing to be able to type in hieroglyphs? No, or Akkadian, like and do Sumerian or sorry, Akkadian numerals. I actually do. Uh, I have to type in cuneiform numerals on occasion, as one does. Okay, but where are we going to put all these things? We also don't have the Cyrillic alphabet or the entirety of the Greek alphabet. There's all of the different Asian languages, both ones that are still currently in use and ones that are classical and no longer used. And that covers the entire world. So Unicode basically extends ASCII to basically throw as many bits at it as you want. So 32 bits would allow us to encode 4 point something billion different symbols. Now, I should be clear, this encodes that it is a symbol. It doesn't encode how the symbol looks. Okay, that's handled separately. So you guys probably noticed this with, well, let's do this to Yik Yak. I did this last semester in 101, and it was kind of funny. So everybody, who has Yik Yak on your phone? Okay, everybody get it on. Okay. And I want you to post a hamburger emoji, right? And that's it. Just a hamburger emoji. Okay, so how does the hamburger emoji look on your phone? Well, how many of you guys are using an Apple device? Okay. What about Android devices? Is anybody doing this on a Droid? Android? You, anybody? No? Okay. Well, anyway, if you have a hamburger emoji and you text it to somebody who's got a Google phone and you've got a Apple phone and you put the two hamburger emojis together, how do they look? They don't look the same. Okay. So the art that's associated with the character and how it's displayed on the screen, that's not part of Unicode or ASCII for that matter. All ASCII does is assign a unique number as a representation of a character. It doesn't say how it's going to look on the screen, right? And this is why, for example, you could change fonts in a document. It's the same letter, it just looks a little different, right? And in some sense, the hamburger emoji looking different on an Android device is like a font kind of thing versus the way the hamburger looks on an Apple device. And don't get me started about the order of the ingredients, right? Who puts the cheese underneath the patty? Like, this is just, no, no. Yeah. Um, Fair. Okay. So, and actually, yeah, Thomas last semester, I'll have to find that link, the experiment thing that so somebody took basically all of the different emojis and the orders in which they stack the ingredients and made cheeseburgers that actually use the ingredients in those orders. And they also, for fun, threw in the order for the Krabby Patty from SpongeBob, and then did a taste test and rated how did each one taste and what was the sort of structural stability of each stacking method of cheeseburger. Uh, yeah, it did, which was surprising because the Krabby Patty order is a little weird by sort of standard methods. So, huh? Apparently. So maybe we could get Sparks to start serving them in the Krabby Patty order. Well, anyway. Um, okay, so Unicode basically solves this problem, and Python is Unicode compliant. So if, for example, um, let's just take the smiley face emoji. You know, I've been picking on the hamburger emoji. It doesn't really matter. Oops, I want, right? There's lots of different ways it'll look. And this particular website, Emojipedia, I kind of like because in addition to, you know, having you being able to search by which emoji you're looking for, it'll even show you how it would look on different devices, right? So how Apple's smiley face looks is sort of this way. And, you know, if you're on Twitter, it looks like that. And, um, they probably have the Discord ones in here. So why is my mouse not working suddenly? There we go. And you can actually copy the character, and I could even put that into um, a file. So in fact, let's just make a new file here. Yeah, so you can do that, right, where it'll and on Mac you can do a similar thing. Basically, a character picker that will let you go in and choose some of these special characters that don't appear on your keyboard. Okay, but for example, here I could just do string equals, you know, the smiley face emoji, and then I could do print the string, and we can see the smiley face emoji here, and we can also see if I run it, it prints in the console just fine. Um, right, so Unicode is fully supported here. Now, that said, do you really need to have smiley face emojis in your programs? Probably not. Okay, and if you start labeling variables with with emoji, I will kill you. Okay, please do not do that. It makes it very hard to read. Yeah. Yeah. So yeah. So don't use emoji for variables. That's bad. Okay. But we can also do this, which is if I print ord of that character. Oops. And I need a parenthesis there. Then what is the number that's attached to that character? In decimal, it's this. So let me print this in hex. Okay, 1F60A. And if I go back over here, then that usually will show you somewhere in here what the actual code is. It ought to. Yeah, here it is, 1F60A, right? And if you click on it, it'll actually take you to the code points, and you can read what other symbols are nearby in Unicode and get a list of those, right? So the number that's associated with it is not something that you necessarily memorize, but you can find it pretty quickly, either in Python or out. So, for example, then this ORD function allows you to take a character and find out the ASCII or Unicode number associated with it. Can you go the other direction? If I give a number, could I see what character is associated with that number? Would be logical to be able to do that, right? And in fact, you can, and you just use the car character. And so let's do 0x1f60 B, which is the one after the smiley face emoji. Okay, so the one that's immediately after the smiley face emoji is, it may be a little hard to see in the terminal there, but it's a smiley face with the little tongue sticking out of the left hand or right hand side. Yeah. Okay. So yeah, you can go both directions with this. So car of whatever makes the character that's associated with that number in Unicode or ASCII for that matter. And you see how I put 0x in front of it? That's because I typed this in hexadecimal instead of decimal. So what's the difference, by the way, between hex and decimal? Yeah. Yeah. Hexadecimal is base 16 versus base 10. And so the symbols, or the digits, if you will, in base 16 are 0 through 9 and A through F. There's a total of 16 of those. Okay. And you guys have used hexadecimal even if you don't realize it. So how many of you guys have had to get your Xbox or something onto the Wabash IoT network? Yeah? How do you do that? What do you have to do? You got to get the MAC address, right, which is a string of 6 pairs of hexadecimal characters, and you have to put those into the website that IT set up, and then it associates that MAC address with your user so that that device can actually connect to the Wi-Fi. You only have to do that, obviously, on like Xboxes and stuff that don't support the enterprise encryption schemes and login schemes, which laptops and real computers do, but your Xbox or whatever won't. So you guys have used hex before, you just may not have realized it. Okay. Okay, good. Question? Hmm? Um, yeah, no, don't do that. Although that said, back in the day, so Thomas said you could use base 6. Nobody in their right mind would actually do that. But there, back in the day, people did use base 8 in computing, and that is called octal. And octal takes 3 bits and associates a single symbol to it, and the symbols there are 0 through 7. I don't think we've used octal since the 70s because it's kind of silly, um, but it was actually used on like PDP-8s and old mainframes and stuff. Question, Armin? Ah, good question. Yes. So ASCII is embedded within Unicode. So what that means is that the letter A character code in ASCII is the same as what it is in Unicode. That's a good thing, right? It means that it's sort of backwards compatible in that sense. So yeah, so very good question. So let's take, for example, um, um, the letter A is, I think, 6-5, if memory serves. Okay, well, we'll find out. No, that's the lowercase e, sorry. So yeah, that is the same as what it actually is in Unicode. Now, if you, for example, let's say that I printed the hex of the word of the letter E, right, it's going to print 0x65. So it has suppressed the extra zeros in the same way that, like, if I asked you to for a number and you said 10,005, you would have to write 10005. But if you said 5, would you write 00005? Probably not in writing, right? We don't write the extra digits in that case. And kind of similar thing here. If you really, really want all the digits, you can get them, but by default, it's going to suppress the superfluous ones. So yes, what that means is knowing ASCII is part of knowing Unicode. It's just the very beginning of it. Okay, so all of the Unicode stuff is just sort of tacked on top of ASCII. That was really smart when they did this to kind of preserve ASCII within it rather than starting over from scratch. Okay, so yeah, so that's just a little bit more about the encoding system. The other thing about that that's kind of nice is, let me go back to the actual ASCII table. And let's just look at the regular ASCII characters. Okay. What's the difference here, oops, sorry, between, say, capital A and lowercase a? Yeah, in decimal it's 32, or in hexadecimal it's 20 or 20, okay? So there's a constant offset between the uppercase and the lowercase letters. Yes? That's really smart, and it's also a very nice offset, which means in our strings function, so let me make another string, and let's just call it hello world, right? What's one of the string methods that we have at our disposal? And I had a list of them here just for posterity's sake. I could do, for example, print string2 dot upper, and what's that going to print? Yeah, it's going to uppercaseify anything that's not already uppercase, right? Similarly, there's a lowercase, and there is a function, I think, that will do the first character of each word. I forget what it's called, but yeah, and so there's a couple of functions that can handle the uppercaseifying, lowercaseifying, and so on. But how do they actually work? Right? What they're doing is looking at the ASCII code for a given character and saying, if it's an uppercase, or rather, let's do the uppercaseifying one. If it's a lowercase letter, make it uppercase by changing its ASCII value. And if it's anything else, just leave it alone. Okay, so if it's already an uppercase character, leave it alone. If it's a punctuation symbol or something else, well, you can't uppercase a period, right? That doesn't make sense. Um, you could, but it's not going to, like, it'll change which code, which symbol it's pointing to, and that's not useful, right? But for the letters, it is. Okay, so in fact, let's actually write a function that will do this, and pretending that we don't have the uppercase function, right? We do. Okay, and so if I write a new function that's going to uppercaseify a string, I should get the exact same result as the built-in function. But in doing so, we'll see, right, how the heck we actually build a string in the first place. Okay, is that okay? Yeah? Okay. And there's nothing special about uppercasing versus lowercasing. I just picked that for sake of example. Okay, good? Okay, so let's go up. You know what, let me just start a new file, and we'll make it just for cleanliness sake, and let's say this is string4.py. Okay, and so I need to define a function that's going to take a string in and it's going to return a string out. So I'm going to add a comment here. It's going to accept a string, uppercase it, and return the new string. Okay, and then in order to call this function, first thing I'm going to need to do is actually have a string. So let me call it string1 is Wabash always fights. and let me call, well, let me just do it this way. Let me print string one dot upper. That's to use the built-in function. And I can also print string, sorry, I'm going to call it what? Uppercase of string one. Okay, so the first one will use Python's built-in function. The second one will use our version. And now we just need to define the rest of our version of the string function. Okay, so is that cool? Okay, so how do we build a string? Yeah. Yeah, we build it by character, and the way that we tack on a new character to whatever we've already done is with a concatenation operation, which is the plus symbol. So it's kind of like addition, but addition of strings. Okay, and in the beginning, do I have a string? Have I built the resulting string? No, because I haven't done anything yet. So let me just call the result equal to a string that has nothing in it. And I'm going to add characters to this resulting string, and that's the thing that I'll pass back to my function. Is that okay? Okay, so the next thing I need to do is I need to, well, if I'm going to do this character by character, what's that sort of tantamount, right? Doing something character by character means what kind of control structure am I going to use to handle this? Some sort of loop, right? For loop would be the logical choice here. You could use a while loop also, but for loop will be the right thing here. Okay, so what are we going to iterate over? We've got two options there. The number of the characters in the string, which we can find that out using the string length function, okay? Or it is possible actually to just iterate over the characters themselves. Okay, now I'll, for sake of demonstration right here, I'm going to iterate over the indices of the characters rather than the characters themselves for a couple of reasons. It doesn't mean that you can't do it the other way. You can in Python, but in other languages, you have to iterate over the indices. You can't do it any other way. Okay, so how many of you guys plan on going on to either CS 241 or 242 next semester? Okay, hopefully a good chunk of you guys. In C, you can't iterate over the characters. You can only iterate over the indices of them. So, and in other languages, it's like that too. So even though it may seem like we're tying one hand behind our back and not using something Python is capable of doing, well, might as well just, I got two ways to do it. I have to pick one. Let's just do it this way. You can also do it the other way. Okay, so for I in range, well, range what? The length of the string, which is len of string. That's the name of the string that's coming into our function. Okay, and so if my string has, let's just say 5 characters, what is its length? 5 last time I checked, right? That makes sense. And so the indices here for my loop, what's the starting value of I? 0. And what's the last value of I? 4, for a total of 5 things, right? So the first character of the string is that thing of 0, 1, 2, 3, 4, for a total of 5 of them, okay? Okay, so then what I need to do is I need to get a character from the string, and I need to get the ith character from the string, and I want to examine it and do something with it. Okay, so for to upper, let's go back to the ASCII table. We need to know, is the character that I'm looking at between lowercase a and lowercase z? If it is, what do we do to it? We subtract 32 decimal or 20 hex from its ASCII code, and that will convert it to the equivalent uppercase symbol. Yeah? What about if the letter or the symbol that we get is not between A and Z? Do nothing, right? You can't uppercaseify something that's not already lowercase to begin with. Yes? Okay, so there's a couple of ways that we can say, is the character in the range of the lowercase letters? So what was the low end of the lowercase letters? The A is 140, oh, sorry, that's octal, 97 decimal or 61 hex. And what's the Z? 122 decimal or 7A hex. So if we're in between those two things, inclusive, so I need to use less than or equals, then that means I've got a lowercase letter. Yeah? Okay. So I need to say if the character string of I is between two values. Okay, so how do I do that? You guys are going to love this, actually. I can actually do that. Okay, so Python does support the ability to compare strings. And what does it mean for a character to be less than or greater than another character? Yeah, the code is in the right order. And now, if you use the comparisons with strings that have multiple characters, what's the order that it uses? It uses what's called lexicographic order. And what is lexicographic order? I know that's a nice. If you can manage to play lexicographic in Scrabble, right? Well, first off, you can't because you need more letters than you get in Scrabble, right? Well, I don't know. If somebody had graphic and you put lexico in front of it, you could score some major points, yo. Yeah. So you could really, really mop up on words with friends with lexicographic. But what does that mean? I'm sorry? Yeah, it's dictionary order, right? So aardvark appears before apple in the dictionary because the second letter of aardvark is an A, and that should appear before a P, right? Okay, so that's what lexicographic order means, is dictionary order. The one wrinkle to the ordering, the lexicographic ordering in Python, is how does a capital A compare with a lowercase a? Capital A comes before lowercase a because it has a smaller ordinal value or ASCII code. Okay. Now, in the dictionary, we don't care, like an actual physical dictionary, we don't care about upper versus lowercase, right? But if we did, then we'd have to choose, is uppercase before or after lowercase. And in Python, because of the way it is in Unicode, uppercase comes before lowercase. Okay, just FYI. Okay. Right. You need to uppercaseify or lowercaseify everything to sort that out. Okay. Okay. So I can do this. And if so, notice that I had to put it together with two individual statements. I need to be greater than or equal to the A, but less than or equal to the Z. And I had to use the word and there. Even though in math class I might have done like a double inequality, you can't do that. Yeah. Okay. And what do we do if if that's the case? If this is true, then I need to tack on the new character to my string. Okay. And so what I'm going to do is I'm going to do result plus something. Okay. So what do I need to tack on to the string? Yeah. Well, yes. Thank you. Okay, but then what am I going to tack on here? What's the new character that I want to put there? Yeah, so what I need to do is to take the character string of I, okay, I need to get its value numerically so that I can take how much away from it, 32 in decimal, and then I need to characterize that thing. Okay, so let's think about the structure of what I did. I took the letter, the character, or gave me its ASCII value, okay, which means, hang on a second, which means I now know the number associated with it. I subtract 32 from it, decimal, that's the offset, and then char makes that back into a character. And then the plus symbol here tacks that on to the result string, which starts having nothing in it. So for the first character, I'm just tacking on something, and that's the new first character, and then I'll do the next one and the next one and so on. Okay, Thomas. Good question. I think it does unless you put in 0x in front. I mean, we're about to find out. Okay. Um, yeah, it should. And the other reason is that ord, okay, is going to return in decimal, not hexadecimal, right? So if it is ornery about hex versus decimal, we'll find out real fast. Okay. Okay, so that's what I do if it's between lowercase a and lowercase z. Does that make sense? What do I do otherwise? Just tack it on, but don't change it. Okay, so what is my else case here? Result equals result plus string of I, and that's it. Okay, so if it's between lowercase a and z, change it, otherwise don't. Oui or no? And that's the last thing, is I need to return the resulting string, which I called result here, just for funsies. Okay, so before we run it and test it and make sure I didn't screw something up, question, preguntas, fragen. Mr. Sparkles, any question, preguntas, and or fragens? 9? You have 9 fragen? No? Yes. So a comma, if there's a comma in the string, will this screw it up? No. Okay, and the reason is because um, the length of the string is going to count all characters, whether or not they're letters, emoji, whatever, right? So it won't terminate based on that. It's going to keep going all the way to the end of the string. Now, that does bring up a good point. There are some languages where um, certain functions within it, when you hit a space or a comma or something, it'll stop by default. You can suppress that. That is the case with, for example, one of the functions that you can use to get user input in C. If you type in a string and there's a space in it, it will stop reading at the space. But in Python, not going to be a problem, either for the input function or for this. I mean, because a comma is a character, it's just not a letter. That's fine. Okay. Okay, good. Other questions, preguntas or fragens? No? All right. Well, let's run it and see if it works. And what is the astronaut's prayer? Please, God, let us not screw this up. All right, and it worked. Okay, so we printed Wabash Always Fights twice. The first version is what? First version used Python's built-in function, and the second one used our function. Okay, so this, you guys probably noticed one of the assignments I posted for next week, the first string processing assignment. So what are you going to do in that one? Well, here we've uppercaseified it. Would it be rocket science to then do lowercase instead? No. Okay. But what would be even more fun? Huh? Okay, that would be a little more fun because you'd have to determine, are you at the beginning of a word to determine whether or not then to capitalize or not. Or even more fun would be, well, how many memes have you guys seen where the text has words, but it alternates between upper and lowercase letter by letter, and it looks ridiculous. Yeah, the SpongeBob, mocking SpongeBob. That is your assignment, is to make a function that takes a string and does that to it. Okay. Um, actually, does the image library support putting text over the image? I know the turtle library does. Um, yeah, maybe we'll do that later. But for now, just get it working in the console. Okay. But yeah, that's basically your assignment, is to write a function that accepts a string and then mocking SpongeBob memifies it. Okay. Now, exactly how you choose to mocking SpongeBob memify it, like, do you want it to make it alternate perfectly every other letter, or maybe throw in a little bit more randomness to it? I will leave that to your discretion. Okay. But do you guys know what I'm talking about when I say these memes? Yeah. Okay. So yeah, make it look like that. Okay. Now, when you do so, are you allowed to use the upper and the lowercase functions that are built into Python? What do you guys think? Maybe. Okay. Deliberately, I want you to not use the functions that are built into Python for your function. Okay. Because it'll be good to have you guys thinking about ASCII and whatnot as you do it. Okay. There's in practice, there's no reason that I should throw that limitation on you, but for the exercise, I think it'll be good to deliberately not use Python's built-in functions, with the exception of the string length function. That's fine. Okay. Um, yeah. Now, if you want to test it and have two versions, one where you manually do it and the other where you use as much as possible of Python's built-in stuff, just to make sure you get the same results both ways, that's fine, right? That's just like smart. In the same way here, that we tested to make sure that I mean, it's obvious if we screwed it up, right? Because it wouldn't be all uppercase, but we've tested it against, hang on, Thomas, against Python's built-in functions just to make sure that we actually are getting the same result. Okay. Now, Python doesn't have a SpongeBob meme function, right? But so write, your SpongeBob version and one that uses the uppercaseify things, and just make sure you get the same results both ways. Okay. Yeah. Yes. Yeah. So if you want to randomize it, and in some cases uppercaseify it and other cases lowercaseify it, and do that in some sort of random scheme, that's fine, right? But so what I mean though, in terms of don't use Python stuff, don't use the dot upper or dot lower methods, okay, except for testing. Okay, is that all right? But yeah, using the random function from the random library, or if you wanted to do things every other character exactly, well, what's the secret sauce there? How can you tell if you're on an odd versus an even numbered character easily? Right. So if you do %2, if you do I%2, what's that going to give you? Either 0 or 1. And if it gives you a 0, what did that tell you about your original index? It's an even numbered position, and otherwise it's an odd numbered position. So if you want to use that, that's fine. If you want to do some sort of randomness, that's fine too. Um, I think most of the memes aren't perfectly alternating upper and lowercase, but they're kind of mostly in that way. And if you really want to have fun with this and maybe show off a little bit, okay, then you can also maybe add a little bit of gamerism to it. So how many of you guys have seen things where people will type like a word and it'll have like 12 exclamation points after it? And then like it'll be exclamation, exclamation, exclamation one, like the word ONE, right? Instead of or like then it'll be the character one because they forget to hit shift when they hit the exclamation symbol, and then they just type ONE for some stupid reason, right? I mean, have fun with this, right? But yeah, make at minimum cool SpongeBob memes. Okay. Um, okay, make sense? Yeah. All right. So let's continue, and I want to talk about some of the other methods that exist in the string library, and also look at a really cool application of one of them that originally started actually as an application in biology, but we can do some really neat things with it with the turtle library also. Okay. And so this is called the Lindenmayer systems. Okay. So the um, the string library does give you a way to do basically a replacement. Okay, so one of the methods, let me just go back to my notes here, allows you to replace all instances of an old substring with a new substring. Okay, so let me just make an example of that and show you what I'm talking about, and then we'll look at another way you can do this. So let's do strings 5.py. All right, so let me make a string. And let me just make it Wabash always fights. Okay. Then I can do the following. I can do string 2 equals, it'll be string 1 dot replace, okay, and then I can change a substring that appears to another substring that appears. So what is a substring of Wabash always fights? Bash is a substring. What's another substring? Space is a substring. So a substring of a string is, well, just a part of that string. It could be as small as a single letter or space, right? That's a character. Or it could be an entire word, or it could be part of the word. Exactly. The whole string is trivially a substring of itself. Um, okay. So I can replace letters here. So for example, I could do, I wouldn't do this in practice. Oh, wrong keyboard. Wouldn't do this in practice, but I could replace A's with A's. And then let me print string 2. Okay. And so what happened to every instance of a lowercase a that appeared? An uppercase A appeared. Okay. Now I did this here with individual letters, but I certainly didn't have to. I could have also done something like um, oh, and I didn't print it. Okay, so I could do that, right, and replace a word. Now, this is just not quite proper, right? Because, but really what should I do then is then string 4 is string 3 dot replace Wabash with, oh, that's one too many. Yeah, okay. And then I could print string 4, right? Okay, so I can replace several times if I want, um, but I'm doing one substring at a time. Okay, does that make sense? Um, so this can be on a letter by letter procedure, or it could be on a word by word or any substring with any other substring. Okay, so is that okay? Now the replace symbol or the replace method, right? Do you think we could write our own function that did that? Yeah, it may be a little tricky, particularly for words, right? As opposed to just letters. But yeah, we could do that, right? The replace is certainly a nice, easy way to do it. Okay. Um, so here, I mean, let's be clear, right? This replacement scheme that I picked for demonstration is rather silly, even though at least with the string number 4, it's 100% correct, right? So um, yeah, even though they have the bell right now. Oh, actually, that reminds me. Sorry. Um, so let me go on a tangent for a brief moment. Um, as you guys all know, everybody and their mother is in academia. Well, professors are all freaked out about what right now? Well, COVID, but yes, also ChatGPT, right? That it's going to put us all out of business. Okay, and it can write your papers for you. Um, and although honestly, if you have a if you're writing a prompt that ChatGPT can write a good paper for your class, then you deserve to get papers written by AIs. Okay. So anyway, yesterday at lunch, a bunch of faculty got together to talk about ChatGPT and implications on our teaching and whatnot. And so one of my colleagues, after the session, he decided to go play with it, and he said, gave ChatGPT make an argument why the Monon Bell belongs at DePauw University. And then it spit out basically a short paper as to why that's the case. Okay. Um, and then let's see. Um, then he put in, let's see. Oh, yeah, he put it in, and it gave the following. The Monon Bell is a symbol of pride and tradition for both DePauw University and Wabash College. However, the bell has been in the possession of DePauw University since its creation in 1887 and has been a cherished symbol of the university's rich history and traditions. Now, that's obviously garbage, and we all know that, but it's an AI. It doesn't know things quite that way, right? So it said, make an argument as to why the Monon Bell belongs at DePaul with an L University, right? The Monon Bell symbolizes the spirit of competition and sportsmanship between two rival universities, DePaul University and Wabash College. And then it keeps going on and talking about how DePaul and Wabash fight over the bell every year. And its display at DePaul University would provide the university with a meaningful symbol of its heritage and foster community and engagement. Um, and then he asked, is DePaul University part of the Monon Bell rivalry? No, DePaul University is not. The Monon Bell is the trophy awarded to the winner of the annual football game between Wabash College and DePaul University. So, yeah, thought that was funny, and you guys would appreciate it. Not in what he sent me. He probably did just as a. Uh, None of you are old enough to know Dr. Foote, but you know how when we do have the bell and before during bell week, it sits at the chapel steps and gets rung between classes? Well, it used to be the case that it was rung 24 hours constantly. Now, why do you think people might be upset by this? It's loud, and if you're trying to teach class and there's this freaking bell ringing in the background, okay, Yeah, well, okay. So then it stopped being rung while classes were actually in session. And then the neighbors complained, and now we don't ring it, basically after what, 11 at night or something? Yeah. So anyway, okay. So back to our string replacement thing. Um, the book gives a really nice example of this, and I've studied these before, but not in the context of turtles. Okay, these things called Lindenmeyer systems. Oh, and of course I misspelled it. Okay, um, or an L system for short. Okay, so the guy who first came up with this was a biologist named Aristed Lindenmeyer, and essentially what he was doing was trying to come up with a way to describe plant growth and as being an expression of a repeated application of a bunch of rules. Okay, and so if we take, for example, um, some trees or plants or broccoli or something like that, right? They have self-similar structure. We call this fractal structure mathematically, but you can describe these as basically just being an application of a bunch of simple rules. Okay, and the way that he did it was by making letters indicate things like go forward or go backwards or turn left a certain amount or turn right by a certain amount. Well, does that sound familiar to our turtle systems? Okay, just in a slightly different way of writing it. Okay, so let's make a very simple Lindenmeyer system. Okay, and let me actually start a new file again just for cleanliness. Okay, and I'll call this L system 1.py. Okay, L for Lindenmeyer. Okay, so let me start with a string which he calls an axiom. Okay, and the axiom is just the starting string, whatever it is. Okay, and just for sake of demonstration, I'll make my axiom just the letter A to begin. Okay, I also need to choose a rule. Okay, and I'll put this as a comment for now. And I can have multiple rules if I want, but I'll just make one rule that every time you see an A, you replace it with ABA. And because I like classic rock or classic music, let's make it ABBA. Okay. Yeah. Okay. Yeah. Okay. So, I mean, it doesn't have to be anything in particular, but I'll just replace it with ABBA. Okay, good. So, the other thing then is I can do multiple iterations of this. So I'm going to make a function that's going to handle the replacement. Okay, and I'm going to call this apply L system, and it's going to apply to a given string, and it's going to apply a given number of times. Okay, good. All right, the first thing I'm going to do is add in a cover my butt statement. And namely, if n is less than or equal to 0, return the string. Don't do anything. Okay, so I'm doing that because I'm about to set up a for loop that's going to depend on the number n. And what would it mean to do a for loop for a negative number of times or 0 times? That doesn't make sense, does it? Okay, so by catching the stupid case of where n is either 0 or negative, then I'm not going to have to worry about that. Okay, does that make sense? Okay, so then I'll do the following. I'll do for I in range n, I'm going to do something. Okay, and let me say my rule is, actually, you know what? I'm going to do string rule and n. And I'll make my rule is that I'm going to replace A with ABBA. Okay, so in this case, the rule is what in my example is just what I'm replacing with. Okay, is that okay? Okay, so well, actually, you know what? Let's do it this way. Let's say I'll pass it rule 1 is what gets replaced with rule 2. That's maybe a little bit better. Okay, does that make sense? So this way I can specify the rule in terms of 2 strings, what it starts as and what it becomes, and then I'm applying this to a string. Okay, is that all right? Okay, so what will I do here? I will do string dot replace, and I'm going to apply rule 1 to rule 2. So everywhere I see rule 1, I'll replace with rule 2. And when that loop is complete, then what do? Return my string. Okay, so let's test this. Let's say new string equals apply L system to axiom with rule 1 and rule 2. And let's just do it once. And then we'll print the new string. Okay, is that okay? So if I do this procedure once, starting with just the letter A and replacing any instance of the letter A with the word ABBA, what should I get back right now? I should get back the string ABBA because I'm only applying the rule once. Is that okay? All right, so let's run it and make sure. And I got A. All right, so why did that happen? No, that's okay, because it should have replaced. No, that's okay. You know what? Just out of curiosity. No, okay. New string is apply L system. Okay, capital A, and I'm replacing the substring A with rule 2 and then returning it. Oh, I know. I didn't do this. There we go. I replaced it, but I never updated, I never stored that result someplace. Right? Does that make sense? Okay. So, yeah. Okay. So if I do this twice, what should I get? Right? I get, so if I just sketch this out, right? The first time I had an A, and then I had an ABBA. Then what happened to each of the A's on either end? They got replaced with ABBA. So I have ABBA, BB, ABBA, right? And this procedure could continue as many times as I care to do it. Okay. So what Lindenmayer did was he thought of letters like A and B or symbols like plus and minus or whatever as being related to geometric things. So A could mean go forward one or some number of units with a turtle, and B could be moved backwards that same number of units. Okay, if we were to apply this to a turtle in that way, then what would our turtle do? It would just go up and back and forth in whatever direction. Okay, so this is maybe not for geometry. This example is not super interesting. Okay, but there are some super interesting ones that the book gives. Okay, so and for sake of demonstration, let's look at one of those. Okay. Now, by storing, and I think I've taken a slightly different approach in terms of implementation than the book did by using the replace function. It's certainly not the only way you could do it, but it is a way of doing it. Okay, so is that okay? All right, so let's make another one. And okay, and in this case, let's also import turtle because we're going to do some turtle stuff. Okay, and let's also copy our our function over here for convenience. Okay, and then we're also going to have an axiom. We'll have a rule. Oops. Ah. Okay, and we'll choose what those are in a minute. Okay, and then we'll have some stuff that will actually deal with the turtle drawing and whatnot. Okay, and I'm just going to use one of their examples for sake of demonstration. Okay. Okay. So I'm going to use the axiom of, let's just do F for forward. And rule one will be to replace any instance of F with F minus F plus plus F minus F. Okay, and the way I'm going to think of this is F will be forward, minus will be a turn left, plus will be a turn right by some angle, and we'll choose that angle later. Okay. Okay, is that cool? All right, now I also need to create a turtle. So let's just get our handy friend Alex, and I also need a window. Okay, and then finally I need to have the turtle.done so that the window doesn't close. Okay, and let's choose here well, let's write the function that's going to actually do the draw the L system with a given string. Okay, so this is a second function I'm going to make, and this is going to be def draw, dang it, draw L system. Okay, so if I want a turtle to actually implement one of these strings, what information do I need? Well, I need at minimum the name of the turtle that's going to do it and the string that I'm going to have him follow. Okay, so let's just call it the turtle and the string. Okay, whatever. Okay, so here, what are the possible characters that could appear in the string that our turtle is going to be executing? Yeah, there's three possibilities: F's, minuses, and pluses. Okay, so I need to have a conditional that's going to catch that and say, all right, if, well, let me actually do it this way. For I in range of length of the string, okay? Because I'm going to have to do this for every character that appears in the string. I'm going to get the character out of the string. Oops, sorry, brackets, not parentheses. So what are the possibilities? A given character could be an F. What else? It could be a plus. And what's the final case? It's a minus, which I can just catch with the else case. Okay, so is that cool? Oui ou non? Okay, so I'm going to basically read the string character by character, starting with the first character. Is it an F? If it is, I'll do whatever an F says to do. If it's a plus, I'll do the plus thing. If it's a minus, I'll do the other. And then I'll just move on to the next character, then do it, and so on until I'm done with all the characters in the string. Okay, that cool? Okay, so what do we want to do if we hit an F? Well, what did we say F was going to stand for? Forward. All right, how much do we want to move forward? That's up to us. 50. Sounds great. All right, so this would be the turtle dot forward 50 units. Great. And if it's a plus, what should we do? Let's go right by some angle. What angle do you guys want to do? I'm going to choose 60 degrees here, but I can certainly change that later. Okay. And so what will happen if we read an F? What should our turtle do? Go forward 50 units. If it reads a plus, it'll turn right by 60 degrees. If it's a minus, it'll turn left by 60 degrees. And I'm going to assume that there's no bad characters in my strings, just for demo. Okay, so I've made the function, but now what I need to do is actually to make the turtle do it. Okay, so for example, if I give draw L system to Alex, and let me just use rule 2, that's string. Or actually, you know what, let me just start with the axiom. Okay, what will Alex do? He will go forward 50 units and that's it. Right? Because what string did I give him? Forward. That's it. Okay? What about if I give him not the axiom, but rule 2? I will now be giving him F minus, F plus plus, F minus F. So I should see forward, left, forward, right, right, forward, left, forward. Okay? Good? So let's see what we get. We get that. Okay, that's cool. Yeah? All right. So now, let's apply. So that's one L system. Okay. What could I do here? Instead of rule 2, what could I do? I could do apply L system to the string axiom using rule 1 to replace with rule 2. And how many times do I want to do it? Let me just do once for right this instant. Okay, so what should I see? Exactly the same thing that I did last time. Yeah? All right. But if I want to spice this up a little bit, what happens if I do it twice? That's cool. Right? Okay. Can't do it 10 times for one important reason. It'll go off the screen the way that I've done it here, okay? I could reduce the size. I could also move where the turtle starts. So let me just reduce the size here to 5, and then I can do it. Well, let's just do 3 and see what we get. Okay, that was maybe a little bit too small, but okay. Well, all right, 5 is a little bit too small, so let's redo it with 10. Okay, and in this case, right, we're only ever moving forward, and sort of because we only ever turn left or right by 60 degrees, and the arrangement of those turns we've put in, we never actually we never really move backwards. Maybe we do a little bit in a few places, but we get this really interesting sort of top part of a snowflake pattern. Okay, and this particular arrangement, this shape, is sort of part of what's called the Koch snowflake, which is a sort of famous fractal. There are other famous fractals you guys have probably seen. Has anybody seen the Sierpinski triangle? Okay, yeah. So how many of you guys have played The Legend of Zelda? Okay, so what's the symbol in The Legend of Zelda, or one of them? The Triforce. So what is the Triforce? Well, yes, thank you, right? But what is the Triforce? It's a triangle that has 3 golden triangles and a black one that's upside down in the middle. Okay, so what about if I said, all right, every time you see a golden triangle, replace it with 3 smaller golden triangles with the black one in the middle? And what about if I told you to keep doing that basically infinitely? You would get this fractal called the Sierpinski triangle. Okay. Yeah, so that's cool, right? And if we think about our rule, or in this case, this is just one rule, right? There's no reason we couldn't have more than one. And we choose what F and plus and minus, and maybe we could add a B in here for a backwards, okay? And maybe tune the numbers and adjust them and stuff. We can make like broccoli looking shapes, or things that look like plants, or interesting geometric fractals like this, or heck, even the Sierpinski triangle, right? Because you've all, like, how would I draw a triangle? Well, if only you guys had already figured out how to make a polygon function. Oh, wouldn't that be great? Yeah? Okay. So this replace and oh my goodness, I am a little bit over. Hang on one second. The replace function that we've done here, what other interesting applications could we use for it? How about encryption? Yeah, okay. So what's the very stupidest encryption scheme that you could possibly imagine? Shifting all the letters by a certain amount. Yeah, that is another stupid way to do it. But a classic example of this was the Caesarean cipher, where you shift all the letters by 13. So A goes 13 letters down the alphabet, B goes 13, and so on. And then when you get to the end of the alphabet, you wrap back around to the beginning. Now, the brilliance of doing it rotating by 13 is to encrypt and to decrypt is the same thing. Because what happens if you rotate by 13 and then rotate by 13 again? You get back to where you started, okay? And that's a really silly way to do it. What's a really smart way to do it? You change you change the rotation amount every letter, which is in some sense what Enigma did. Okay, yeah. Yes. Now that would be diabolical, okay? Because, well, yeah, it would be. But yeah, you can use these replace techniques for encryption. And we'll maybe talk about that next time. All right. Thank you for letting me go over. Go to chapel.